Good morning to your class. That is, we are continuing the network analysis and we are continuing the project crashing portion. Now, in this case, we are showing that as previously discussed about the cost slope, we calculate the cost slope by dividing the difference between the crash cost and the normal cost, and then divided by the normal time minus and the crash time. Now, in normal time is always higher than the crash time, and the crash cost is always higher than the normal cost. Now, we do that when we are doing that. The slope of the line, that is how the way the line slants down, that means the crash cost is higher and the number of days is lower, and the normal cost is lower but the number of days is higher. So the crash point is at a higher point in the graph and then the normal point. So likewise, there are different lines or different activities, or different graph of, or different activities. And to also understand the project activity, you can speed up the project activity to a certain degree by some number of days to complete by some number of days when we are crashing a certain activity. But but we have to remember that we cannot eliminate the activity. We can only reduce the number of days for that activity. Now, when you are, so that means say a certain activity, say A to B, it is mm, taking us say n number of days. So when we are getting for that n number of days, when you are getting that n number of days, um, say 8 days, say activity A to B is in 8 days, and the before crashing, and after crashing it is say 6 days. So we are saving those 2 days, but we are not eliminating any activity. So we are just reducing the time limit so that we can complete the whole work within a lesser amount of time. Now, when we are analyzing the crash options for the project activities, the object is to find out the time and cost rate trade-offs. Now, what is time and cost rate trade-off? Now, time and cost rate trade-off means that the cost slope, or the difference in the amount of the cost divided by the difference in the amount of the time. This is the formula. So now what will be the result of that? We will determine which activity is likely to be crashed. Now we take a normal network diagram. Say activity is A, B, C, D, E, F, G. Now we have the predecessor activity. Now, as we can see and know that activity A is the starting activity, and activity G is the ending, is the final activity. So activity A does not have any activity previous to it, and activity G does not have any activity that is after that. So activity A to activity G, activity A doesn't have a predecessor, activity B doesn't have a predecessor, it is independent of activity. You have to use a dummy activity. Activity C has a previous activity, activity A. Activity D has a previous activity, activity B. Activity E has a previous activity, activity B. Activity F has two previous activities, C and D. And activity G has a previous activity, activity E. Now we have the normal time. What is the normal time? Normal time, as we know from our previous week's lecture, that normal time is the expected time, which is the calculated average time between the optimistic time, the pessimistic time, and the maximum time. So we divide this, that is expected time is equal to t expected time, or normal time is equal to the optimistic time plus 4 times the average time plus the pessimistic time whole divided by 6. This gives us the normal time. Normal time for activity A is 2 days. Now crash time, if we are going to crash that job, or we are going to reduce the time in that job, it comes down to 1 day, and the normal cost is 10,000 rupees for activity A. However, when you are crashing a job, the time goes up, it is 15,000. or 5,000 more. So likewise for activity B, the normal cost is 15,000 and crash cost is rupees 21,000. For activity C, the normal cost is 20,000 and the crash cost is 24,000. For activity D, normal cost is 7,000 and crash cost is 7,000. For activity E, normal cost is 8,000 and crash cost is 15,000. For activity F, normal cost is 10,000, crash cost is 16,000. For activity G, normal cost is 12,000 and crash cost is 36,000. Likewise, for activity B, it reduces to from 8 days to 5 days. For C, 4 days to 3 days. For D1, the activity does not change, the crash time does not change because the minimum number of days is 1. For activity E, it changes from 2 to 1 days. For activity F, that is 5 to 3 days, and activity G, it is 6 to 2 days. That is 4 days is the maximum. Now we are starting the activity. Now node 1, it has two activities A and B. Since both the activities, as we see, they do not have any predecessor, so they can start at the same time. There is no activity before A and B. So A and B, we are having two different activities. Now activity C has a predecessor activity A, so we are having A in front of a C, and activity D has predecessor as activity B. So activity D is in front of is after activity B. Activity D is after activity B, and activity E is after activity B, whereas activity F is after activity C and D. So activity F is after activity C and D. Say we are meeting C and D at node number 4, then you are having activity F, and then we have activity E after activity B, activity F after activity C and D. So activity F after activity C and D, number 6 is the end, and number 5 we have activity E is G. So activity E is G. So the final work ends at from node number 1 to node number 6. Now we can check the critical path. The critical path ACF is 11, BDF is 14, and BEG is 16. So we have the critical path as 16 days because activity BEG takes the maximum number of days, that is 8 plus 2 plus 10, 16. Now we have the activities A, B, C, D, E, F, G. Now we have the normal time, we have the crashing time, we have the normal cost, and we have the crash cost. Now this is the very normal simple form of this particular table. Um, Now what we have done here is we have calculated the activity normal time and the days crash time from this table, and we have taken the number of days time savings, that is activity A 2 to 1 days, 1 day is saved. Activity B 8 to 5 days or 3 days is saved. Activity C 4 to 3 days, 1 day is saved. Activity D 1 to 1, no days are saved, so we cannot crash that activity. Activity E 2 to 1, 1 day is saved. Activity F 5 to 3, 2 days is saved, and activity G 6 to 2, 4 days is saved. So we can save maximum number of 4 days and we can save minimum number of 1 days. But however, this depends on the crash cost. Say activity A normal cost is 10,000, activity crash cost is 15,000. You can check from the previous table. Activity B normal cost is 15, crash cost is 21. Activity C normal cost is 20, crash cost is 24. Activity D normal cost is 7, crash cost is 7, so there are no savings. Activity E crash cost is 8 and normal cost is 8 and crash cost is 15. F normal cost is 10, crash cost is 16, and G normal cost is 12 and crash cost is 36. So we have the total number of savings, which is crash cost minus normal cost. So that is 15,000 minus 10,000, 5,000, 21 minus 15 is 6,000, 24 minus 20 is 4,000, 15 minus 8 is 7,000, 16 minus 10 is 6,000, 36 minus 12 is 24,000, and so on. Now we have the network analysis, that is days savings from this table, not time savings, and we have the cost savings. We are dividing cost savings divided by the time savings. Now we are here to calculate the minimum that is available. The minimum cost group is 2,000 for activity 3. So we are going to crash the activity for which the cost is minimum. The cost is minimum is for activity with the second activity or activity number B. Thank you. We have all, this is all in project crashing analysis. However, what we do network analysis, calculate the cost slope. We crash the activity with the lowest cost slope. In this case, it is 2,000. We recalculate the critical path method, because once we are doing a crashing, we have multiple critical path methods, and we generally generally crashing causes multiple critical path method. We then have to calculate the crashing using you have to then use crashing technique for all those critical path methods again and again until we have the critical path method that all the paths are giving the same number of days, or we have any single critical path method. Thank you. This ends our class on project crashing.